This video is a discussion of the solution to question 3 part B from the 2018 Mathematical Methods exam paper. So we'll have a look at the exam paper itself to start. So this is question 3B here. The question starts by telling us what Green's theorem is. So it says, this is just a declaration of Green's theorem here at the start. Green's theorem says if C is the boundary curve traversed counterclockwise of the simply connected region R, and functions P and Q have continuous partial derivatives on C and R, then the following equation holds. And this is a nice equation. It relates together the two types of integration we saw in this course. Path integrals, the integral on the left, the integral along the path C of p dx plus q dy, that linear differential form, and that is equal to the double integral over the interior of the region R of this difference of partial derivatives dq dx minus dp dy. Now it's important to realize that we aren't being asked to give the proof of the general theorem here. We're merely being asked to verify it in the special case of this pair of functions p and q. So p of xy is the product x times y, q of xy is x squared times y, and the region we're talking about is the triangular region with those three vertices there, the origin, 2, 0 and 1, 1. So let's see how we would treat this question. So I'm going to begin by sketching the region R, just so we can see it in front of us and we can think clearly about it. So we've got these 3 points. We've got the origin here, the point 2, 0, which would be here, and the point 1, 1, which would be about here, let's say. So it's this triangular region formed by these two slanted sides and the x-axis. Now we're going to start off by looking at the integral. I'm just going to call it I. It's the integral along C of p dx plus q dy. So to verify Green's theorem here, of course, we're going to evaluate the integral on the left-hand side, which is this integral here, work that all the way to a numerical value, and then secondly evaluate the integral on the right hand side, work that all the way to a numerical value, and we expect the two values to be the same at the end. Now for performing this integral we have to integrate counterclockwise, anti-clockwise around the boundary of this triangle. Of course the triangle is very obviously made of 3 separate straight line segments, so we're going to break those, we're going to consider each of those straight line segments in turn. So you can express the boundary curve C as C is the sum of these 3 curves. When you're summing by adding curves here, we mean concatenating them, running one curve after the other. So C1 plus C2 plus C3. And if I do that, then I can break down the integral. Okay, because the property of integrating along curves is that if you break down the whole curve into different parts, one after the other, you can break down the integral as the sum of the integrals over those individual parts. So this is going to be the integral along C1 of p dx plus q dy, plus the integral along C2 of p dx plus q dy, and along C3 p dx plus q dy. So I've got 3 subintegrals to evaluate here. Just to make it easy to refer to them, I'm going to call this I1, this one I2, and this one I3, just so I can easily refer to them. So in order to do this, we need to get some detailed information about what's happening on the 3 curves. We want to identify the correct equations for those 3 curves, and how we're going to parameterize them, which of the variables x and y we're going to take as the fundamental one. So examining the curves here, what we find is, well, along C1, so the equation for C1 is, of course, y equals 0. It's the x-axis. As a consequence of that, the differential dy is 0. And which bit of the x-axis are we talking about? Well, x is beginning at 0 and increasing to 2. So that's all you need to know about that integral. So the y's will disappear, so to speak. Along C2, so what's happening on C2? C2, so which line is this? It's the line with slope -1, and it's got intercept, that would intersect the y-axis at 2. So this is the equation y equals minus x plus 2. Minus x plus 2. As a consequence of that, the relationship between the differentials is dy is equal to minus dx. And it's probably easier to put everything in terms of x here. So which bit of this line are we talking about? Well, x begins at the value 2 and descends to 1. Okay, that's all the necessary detail for the curve segment C2. And finally C3, it's a bit more straightforward. It's the line y equals x. It's the equation of this line C3. The relationship between the differentials then is dy is equal to dx. And which bit of this line? Well, x begins at 1 and descends to 0. Okay. So now we can launch into each of the 3 separate integrals. So I1, I won't repeat it here. This is I1 here. What are the curves P and Q? The curves P and Q. Let's put these up the top here. So Pxy is simply the product x times y. Qxy is x squared times y. Okay, so taking this integral p dx plus q dy, well, y is equal to 0, so we're integrating x from 0 to 2. So p is x times y, so it's simply x times 0 dx. Then plus q dy. Well, q is x squared times y, but again y is 0, and the differential dy is 0. So these are limits for the integral x, of course, but this is just 0. It doesn't survive, and of course this is all 0 as well. So you're just integrating 0 here. So the whole thing is just 0. So actually, the integral along C1 doesn't make any contribution to the overall integral because it's just identically 0. Okay, we'll proceed on to the second one, which is this integral here. So to tread a little bit more carefully here. So we're converting everything to x, so we can stick with our limits for x. So x begins at 2 and ends at 1. Then I got p dx. So p is the product x times y. So I've got x times y, but I don't write down y because on the curve C2, y is always minus x plus 2. There's minus x plus 2 here. And this is with respect to the differential dx. And then I have plus q dy. Q is x squared times y, but again y is minus x plus 2 on this curve here. And the differential dy, I replace that by minus dx. Okay, so that's everything successfully converted to be in terms of the x variable. Before evaluating this now, I just need to tidy it up a bit. So it's going to be an integration, an integral of a polynomial. So which polynomial? Well, so we got x cubed terms here. So we got minus x cubed from this product here, but then it picks up another minus sign here. So it's in total it's x cubed. I've got a minus x squared from the first term and plus 2x squared, but of course there's the minus sign there, so it's actually minus 2x squared. So we've got minus x squared minus 2x squared, so we've got minus 3x squared. And then finally we've got this 2x here. So those are all the parts of the polynomial, and I've taken proper account of this extra negative sign here, so this is all integrated with respect to x. Okay, so now this is, a very familiar looking single variable integral. So we can just go ahead and integrate it quickly. X cubed integrates to x to the power of 4 over 4. Minus 3x squared goes to minus x cubed. 2x integrates to x squared. And this gets evaluated at 2 and 1. Okay, let's forge ahead here. When you substitute in x equals 1, you get 1/4 minus 1 plus 1. And then you subtract the evaluation of 2. When you evaluate at 2, you get 2 to the 4, which is 16 over 4, minus 2 cubed, which is 8, plus 2 squared, which is 4. So what is this? Well, first bracket is just 1/4. Second bracket is 4 minus 8 plus 4. So the second bracket is 4 plus 4 minus 8. So the second bracket is 0. So the whole thing is just 1/4. Let's go to 1/4 for our second integral. Okay, so let's do the third one, I3, which is this integral here, the integral along C3. On C3, x begins at 1 and ends at 0. Then we've got p dx, so p is x times y, but on C3, y and x are the same. So this is simply x squared dx. And then the second term is q dy. So q is x squared times y, but on C3 y is the same as x, so this is x cubed. dy, well, the two differentials dy and dx are the same on C3. Okay, so this is simply the integral from 1 to 0 of the polynomial x cubed plus 2, plus x squared, excuse me, with respect to x. So this integrates, of course, to x to the 4 over 4 plus x cubed over 3, evaluated at 1 and 0, like that. So, of course, when you evaluate at 0, you get 0, and you evaluate it at 1, you get 1/4 plus 1/3. So this is minus 1/4 plus 1/3. 1/4 plus 1/3 is some amount of 12. So you got 3/12 plus 4/12, so 7/12. So we've got minus 7/12 in total. So how are we doing? Okay, we got I1, I2, I3. So we can. So finally we get I, the integral we wanted, I as it's I1, which is 0, plus I2, which was 1/4, minus 7/12. So what's this? 1/4 is 3/12. So it's 3 minus 7, so it's minus 4/12. Otherwise known as minus 1/3. Okay, so we're halfway there. We've got the left-hand side of Green's theorem. The left-hand side of Green's theorem, this integral here, we have this as minus 1/3. So now we go and evaluate the right-hand side of the integral, and it's a good consistency check here. We better be sure we get the value minus 1/3. So, the right-hand side of Green's theorem is this integral here. So it's this double integral, the double integral over R of the difference of the partial derivatives dq dx minus dp dy. And this is dx dy like this. Okay. So how do you start evaluating something like this? Well, we can work out this difference of partial derivatives fairly easily. Dq dx, well, dq dx is 2xy minus dp dy. dp dy is simply x. So this is the integrand. This is what we're integrating. And the meaning of a double integral like this is it's actually a what you might call a repeated integral. So it's one integral inside another. Now we're free to choose the ordering, which differential goes on the inside, which on the outside. That has an influence over what the exact limits of integration are. But I think for this one, the way to go would be to keep dx as the inner integral, and then dy is the outer integral. So this is what the integral is, except I haven't filled in yet here what the four limits of integration are. So to identify the four limits of integration, you need to come back to your sketch of the region. So R is the interior of this triangle here. And we begin on the outside and work our way in. We got the y variable on the outside. So you look at your region R and you ask yourself, of course this is the y-axis here, this is the x-axis. Between what limits of the y variable do you need to integrate in order to capture the region R? So you need to begin at y equals 0 and integrate all the way up to y equals 1. Okay? The region R is within this horizontal band from y equals 0 to y equals 1. Okay, so we integrate from 0 to 1 with respect to y. And what are the limits on the x variable? Well, it depends. It depends on what y is. For low values of y down here near 0, you've got quite a long interval for x from close to 0 up to close to 2. But as y gets closer to 1, the interval for x becomes shorter, and it becomes something close to just below 1 to something just above 1. Okay, but we need to describe that exactly. So for your typical value of y here, we want to integrate along the x variable, so we just pick up this line of points here, okay, which are all at the level y. But what are the x coordinates here? Well, of course, they come from the equations of the curves C3 and C2. So we're always starting at the corresponding x coordinate of this point from C3 and integrating all the way up to the x coordinate at this point on C2. C3 is this equation y equals x. So this x coordinate here is actually y. So it's still a point. If this is the level y here, this point here is y on the x-axis as well. So we're integrating from y here. And what's the upper limit? Well, if this vertical coordinate is y, what's this point here? What's the x coordinate of that point there? Well, you look at the equation for C2. It's y equals minus x plus 2. So make x the subject. So it's x is 2 minus y. So if this point has vertical coordinate y, it's got horizontal coordinate 2 minus y. There. Sorry it's so small, but the upper limit there of the integral is 2 minus y. So it's always worth taking your time on getting these limits of integration right. It's sensitive to how you're ordering the variables. So if I had y as the inner integral, and x as the outer integral here, I'd get quite different things here. In fact, I'd have to split the integral up into two double integrals, because when you're specifying an x value for values of x beneath 1, the integration is ending on C3, but for values of x above C1, the integration is ending on C2. So you have to separate the double integral into a sum of two double integrals, one for the left-hand portion of the triangle, one for the right-hand portion. But sticking with this ordering here, with x on the inside and y on the outside, we avoid that complication. Okay, well, everything's ready. We can just forge ahead with the integration. So we perform the inner integral first. So we leave the outer one alone. Integrating with respect to x, be clear on the variable you're integrating with respect to. So integrating 2xy with respect to x. Integration is linear, of course, so we just do it term by term. So the integral of 2xy with respect to x is x squared y. And the integral of minus x is minus x squared over 2. And that gets evaluated at, I'm going to write here x equals y and x equals 2 minus y. So these are limits for the x variable that we're going to put in. And I've still got the differential dy here. Excuse me, I'm just going to wake up my computer. Okay. Okay, so let's do this evaluation here, or in fact, just to make it a bit control the length of it, factor out the x squared bit. Yeah, so this is x squared into y minus a half. Yeah, just organize it a bit better. X equals y, x equals 2 minus y dy. So this becomes the integral from 0 to 1 of 2 minus y all squared, and I'll factor out the y minus a half, and then I minus y squared. Okay, so all of that then is multiplied by y minus a half. Okay, I'll drop that square bracket there, don't need that. And I've still got the differential dy here. So it's reduced to the integral of some kind of polynomial with respect to y. Okay. So let's just start working this out, tidying this up. I've got integral 0 to 1 here. So first work out what's inside the curly bracket here. I've got y squared, but then minus y squared. So the y squareds cancel out nicely. I've got minus 2y doubled, so I've got minus 4y, and then I've also got a 4 from the square of 2. So I've got 4 minus 4y, and that's still multiplied by y minus 1/2 dy. So just multiply these out here, and when you multiply these out here you get minus 4y squared minus 4y squared plus 6y. So we've got 4y plus 2y, so we've got plus 6y, and then finally we've got 4/2, so 2, but minus 2. Okay, and this is all integrated with respect to y. So I might just about fit it into the bottom of the page here. So this integrates to, coming over here, integrating this, we've got minus 4 over 3y cubed plus 3y squared minus 2y. Evaluated at 0 and 1. So thankfully we're getting some amount of thirds here, because remember this is supposed to work out at minus a third, so it's looking good. So I've got, of course, when you evaluate at 0 you get nothing, so there's a factor of y and everything. So evaluated at 1 we get minus 4/3 plus 3 minus 2. So what's this? This is minus 4/3 plus 1. Minus 4/3 plus 3/3 is minus a third. So yeah, this is the value of the right-hand side of Green's theorem. And of course it's the same as we expected it to be as the left-hand side. Okay. So rather than turning the page, just as a conclusion here, we did find that the left-hand side was equal to the right-hand side as expected. Okay, so we have indeed verified Green's theorem for this linear differential form, these two functions p and q, and this triangular region R. And along the way there, what we've demonstrated is our ability to do integrals along curves and our ability to do double integrals. And it demonstrated our understanding of Green's theorem as well. Okay, hope you found that useful.